Okay, hopefully we have sound here. So, yep, we have audio and video. Okay, this is our last day of kind of new material. Still looking at conservation of momentum today. And I wanted to do a couple of problems that are two-dimensional as far as how they work out. I didn't track down any of the ones that are on the online sapling assignment, but I did put some on there that are two-dimensional, although they're two-dimensional and completely inelastic, which means the two objects stick together after the collision. So I'll show you how to do those things, and we'll see how it works. So I want to share the screen here to that, and it should be kind of blank now, except for what's bleeding through. Okay, so in our collision problem here, we can come up with a bunch of different scenarios for these, but let's just suppose that we'll start off with two things that are going to meet at right angles. And so this is the path of one of them. And I'm just going to put an arrow or a 1 above that one. And then we'll have another thing that's coming down from this direction. And this will be object 2. And they're going to meet at this point right here, even though it doesn't look like it. So that'll be the case. And this is a right angle here. So we'll have that. So let's suppose that object 2 has a mass of, we could actually start with these things being small objects, like maybe they're on an air hockey table. So this might have a mass of 0.150 kilograms, which isn't very much. Okay, it might just be a little bit of a weighted air hockey puck or something like that. And its initial speed before this collision, actually we'll give it a velocity here. Well, let's just give it a speed, and we can see the direction it's going and figure that out later. But let's suppose it's just going at 3.55 meters per second. And then object 1 is something of a comparable mass, but M1 is 0.225 kilograms, which actually makes it about 50% more massive than that one. And V1 is going to equal, let's see, this is the direction of V2 down in that direction. This will be the direction of V1 in that direction. And V1 could be 2.95 meters per second. So we have that. And you can see the directions of those velocities. And here's the condition. The objects stick together after the collision. Whoops, I did not want to write there. Oh well, I'll stick another piece of paper there. After the collision. What is their final speed and direction? Okay, so that's what we have to figure out. Well, momentum is conserved in collisions. And so something I can say is that m1 v1, which is the initial momentum of object 1, plus m2 v2. Now I've got arrows on top of these, which means these are both vectors and their direction is going to have to be taken into account. That's the total momentum before the collision. So total momentum before. That has to equal the total momentum after the collision, because momentum is always conserved. So here's our total momentum after. Well, here's the thing. After the collision, we're going to have some object that's the two of these things stuck together, so its total mass is going to be m1 plus m2, and it'll have some velocity v final that we haven't figured out yet, but it's going to look like that. Okay. Well, we've got enough information to figure this out. Okay. If I let the x direction point to the right and the y direction point up, so there's my coordinate system, I can say that m1 v1 is going to equal m1 v1, the magnitude of v1, in the x hat direction, and m2 v2 is going to have a minus sign in front of it because it's going in the minus y direction, plus m2, the magnitude of v2, in the y hat direction, and the minus sign just tells me that it's headed down. Okay, and this is still going to equal m1 plus m2 times v final. Okay, well, I can just solve this for v final by dividing both sides by m1 plus m2. And this is just an expression of conservation of momentum expressed in abstract mathematical stuff, and that's kind of what we've got going here. But what it tells me is, if I divide both sides by m1 plus m2, I'll have m1 v1 divided by m1 plus m2 in the x hat direction. That'll be the final momentum going to the right, and I'll have minus m2 over m1 plus m2 times v2 going in the y hat direction. And I can figure out each of these because I know all the numbers. I know m1, I know m2, I know v1, and I know v2, and that will equal v final. Okay. So let's see what they come out to. It's a matter of substitution at this point. And I may have made up a problem similar. I think this is pretty similar to the two-dimensional ones that are on the homework assignment. Well, let's see, this first thing, m1 v1 over m1 plus m2 is going to equal, m1 is 0.225 kilograms, and v1 is 2.95 meters per second. And then the sum of those two, 0.225 kilograms plus 0.150 kilograms. Okay, unit-wise, when you add things together, they have to have identical units. I'll have kilograms on the bottom. I've got kilograms on top. Those will divide out, and I'll end up with just meters per second. And what this number is going to be is the component of the final velocity that's in the x hat direction. So, okay, where did I take it? There it is. oops, back. Being careful to wrap the denominator in parentheses. Oh, 0.225 plus. Okay, and this is just arithmetic at this point, or algebra, I guess, I don't know. But I get 1.77 meters per second. Okay, so that'll be what multiplies the x hat part. Now it asks for the final speed and direction, so I can't really say anything yet, but I do know that v final as a vector will equal 1.77 meters per second in the x hat direction, minus, I haven't calculated the y one yet, but that one will be m2v2 over m1 plus m2, which is going to be 0.150 kilograms times 3.55 divided by m1 plus m2 again, 0.150 kilograms. I've got them in the wrong order, but addition is commutative. And this will equal, it's just a matter of plugging and chugging on here. Making sure you wrap that in parentheses. Okay, and for this one I get 1.42 meters per second. Now remember, that's just the number part. Its direction is in the minus y hat. So I'll have minus 1.42 meters per second in the y hat direction. So I could kind of sketch this. The v final, let's see, it's going to be 1.77 meters per second out here. There's the x component, and here I've got 1.42 meters per second. And the magnitude of those two, they're perpendicular to each other. So I can use the Pythagorean theorem to figure that out. And so just take the square root of, this would be v final. I think that's what I called it. Yes, I did. The magnitude of v final will equal the square root of 1.7, clear that, second square root of 1.77 squared plus 1.42 squared. I think I did everything right, which is 2.27. So the magnitude of v final, which is the speed, is 2.27 meters per second. And then the direction, I can figure this out. Okay, that angle theta is going to be the inverse tangent of the opposite side divided by the adjacent side. And I've noticed on your test work, several of you are writing so ka toa. Tangent is the opposite over the adjacent. It's just stuck in my head. I'll never get it out of there, I don't think. I'd probably misspell SOHCAHTOA before I got the fact that I have it memorized out of my head. But anyway, inverse tangent. Nice thing about this calculator, to get the inverse tangent, you just push the tangent button twice, and I've got it there. So opposite over adjacent, 1.42 divided by 1.77. And I get 38.7 degrees. So the final velocity is 2.27 meters per second, and the angle is 38.7 degrees below the x-axis. And you could say below the positive x-axis. And that's a complete description of the final velocity of the thing. So after they stick together, that's how you can figure it out. Let's do a car collision and have a collision between two cars. And I actually have a friend who this happened to. He was driving a Prius in downtown Moses Lake, and he was on Alder Street, stopped there at Broadway, and or no, actually he had a green light on Alder Street crossing Broadway, and his car got T-boned by another car. And we'll just make up some weights for the cars, or I'll find some for the cars. Go over here. We'll share our screen with my, where is it? Maybe I don't have it open. Yeah, I do. Okay, Nova Videos. I'll start a new thing. But that's what we're going to share with. Anyway. I don't know what we're going to see here. Anyway. Prius weight. How much? 3,010 to 3,220. Let's take 3,200 pounds for the Prius weight. And then what should we have it hit by? How about the most common car on American roads? An F-150, and we'll just give it something in the middle there, 4,500 pounds. We won't add to it the full load of firewood that it happened to have or anything like that, or pretend that it didn't for the sake of the poor guy that's going to get T-boned by this. Then we'll go back to our share here and share that again. Okay, now those are weights. We're going to have to convert those into masses, but it turns out the masses are proportional to the weights. But still, just for good form, we'll figure these out in masses. So I'll take my the weight of the Prius, which is the mass of the Prius times G, is equal to 3,200 pounds. But I'm going to multiply that by how about 4.448 newtons per pound. And I'll get that the weight of this car in newtons is equal to 14,200, or we'll just say 14,000 newtons, and that's mg. Then the mass of the Prius is just going to be that 14,000 newtons. This is kind of test review too at the same time for the final test, which is the next one we have. 14,000 divided by 9.8. We'll just go with 9.8 meters per second squared today. And I get about 1,500 kilograms. Okay, so that's the mass of the Prius. I'll do the same thing for the F-150, and I'm just going to go through the calculation. The mass of the F is what I'll call it, rather than anything else, multiplied by 4.448. And divide by 9.81. And I get about 2,000 kilograms. This is kind of surprising that the F-150 is not all that much heavier than the Prius happens to be. Hope I punched in the number right. Yeah. All right, now let's suppose we've got the Prius that's going in this direction at, maybe it's only going at 25 miles per hour. And then the F-150 is coming along here, and they're going at 30 miles per hour because they're on Broadway and carefully observing the speed limit, although they're not carefully observing the fact that they're running a red light. And these are going to collide in such a way that they get T-boned and stick together after the collision, at least initially. So we'll see what happens in this place. Final speed and direction is what we want. Yeah, that's what we want. Well, let's just let X point in the direction that the F-150 was going. This is, oh, I meant to put 30 miles. Anyway, this is the F-150 there. So that's the X direction, and just let Y be the direction of the Prius, or we could have called this east and this north. In fact, what if we do that? That won't hurt. East and this is north. So what we'll have is the mass of the Prius times the initial velocity of the Prius is going to equal, whoops, it's not going to equal anything. If I add that to the mass of the Ford 150 plus the initial velocity of the Ford 150 is going to equal, this is the initial momentum, it'll equal the final momentum, which is going to be the Prius and the F-150. And then instead of having a V final on this one, I'm going to call it V sub W for the velocity of the wreckage. And the Prius was totaled. I don't know about the F-150 at all. So we'll do the same thing we did last time. We'll figure out the components of the final wreckage velocity from this. Now I can write each of these in terms of some unit vectors that point, one of which points to the east and one of which points to the north. And the unit vector for this first one would be, I'll multiply just the speed of the Prius times the, that one's going in the n hat direction. So n hat is just a unit vector, a vector with a dimension of 1 or a length of 1 that points north. And to that, I'll add that of the F-150 and mass of that, the initial speed of that, and it's going in the E hat direction towards the east. Okay. And going to save myself a little work. I'm going to divide each one of these things by the total mass of those two things. So mass of the Prius plus the mass of the F-150, divide this one by the mass of the Prius, times the mass of the, whoops, times this, no, yeah, plus the mass of the F-150. I don't know why I was thinking 2 steps ahead is what I was doing. The denominators are the same in both of these things. And that'll equal the velocity of the wreckage. Okay, so this isn't too bad. We're adding 2 vectors together and getting a single vector out of that. And we want to know what is the final velocity. Actually, we're going to want to know the final speed. Now, on those velocities, I'm going to have to do a little bit of unit conversion. And that seems to always be the case. Let's see if I got part of a sheet I could use. Yeah, this one will work out okay. 25 miles per hour times 1,609 meters per mile. By the way, when you're doing unit conversions, if you're going from miles to meters, it's best to use an MI for the miles. Otherwise, you can get confused. And then times 1 hour over 3,600 seconds. So this is the initial velocity of the Prius. So 25 and you get about 11 meters per second. So good enough. And the car was going 30 miles per hour. Same conversion, 1,609 meters per mile times 1 hour over 3,600 seconds. And I'm just going to go back up to the previous calculation and change 25 to 30. Or I could have just multiplied it by 6/5, I guess. And I get 13 meters per second. Two significant figures anyway. Now, these aren't going to be perfect because we only have 2 significant figures, but at least we can plug in everything we need to now. So the VW is going to equal mass of the Prius, which was 1,500 times the initial speed of the Prius, which was 11 meters per second. And then on the bottom, I want the sum of those 2 masses. Is it okay if I just add them in my head? 3,500 kilograms. Now that's in the n-hat direction, plus mass of the F-150 is 2,000 kilograms times that of the F-150, which was 13 meters per second. And then on the bottom, again, the 3,500 kilograms. And that's in the E-hat direction. So it's a matter of calculating now. And we can do that. I will get the velocity of the wreckage is going to equal 4.7, whoops, forgot an equal sign, 4.7 meters per second in the n-hat direction, plus 1,500 times 11. Yep, that works. .4 meters per second in the E-hat direction. Whoops, E-hat. Yeah. So there's our Final velocity. Notice it's less than either one of the initial two velocity components, because the thing that was headed east has now acquired an additional 1,500 kilograms of mass, and so that the momentum toward the east stays the same, but it's now got more mass, so it has less speed. And the same with the momentum toward the north. Same thing's going on. In fact, that one drops by a bigger factor than the momentum toward the east, because this was only a 1,500 kilogram car and it picked up 2,000 kilograms of mass. Going north, the northward momentum stays the same as what it was before as well. Okay, and then I can make a sketch of what those look like. We will have 4 meters per second to the east, and to that we will add 4.7 meters per second to the north, E hat and N hat, and whoops, missed. Oh well, theta. We'll have a VW, that'll be the magnitude of the velocity of the wreckage. So VW will equal the square root of 7.4 squared plus 4.7 squared. Which is going to be looks like about 3.5. Whoops. Something went haywire with my calculation here. I better redo that. I don't know if I forgot to put a decimal point on one of those things or not. Oh, I multiplied them instead of adding them. That'll make a difference. Okay, this is better. I get 8.8 meters per second. And then that direction, theta, is going to be the inverse tangent of the opposite 4.7 divided by 7.4. And you could write in the units here, but they're going to divide out when you're taking a ratio of things that have the same units. So again, just hit my inverse tangent, and 4.7 divided by 7.4, and I get about 32 degrees. And what I would say, the way I would describe this, if you just say 32 degrees, measured from what? And I would say 32 degrees north of east. Okay, because east is that way. And if you go north from there, you're rotating in that direction. So you'd rotate 32 degrees north from east. Okay, so that's a couple of two-dimensional problems there. And you have to set up an expression that ends up having the initial momentum. You add the momentum of one to the momentum of the other, and that'll equal the momentum of the stuck together things after the collision. And I think there are 2 or 3 of those that I put on the homework, on the sapling homework. So give those a shot. All right, well, let's try another collision here. I want to show you something about elastic collisions in one dimension. that may help you with some of the problems that you might have. And we'll imagine that anyway, elastic collisions in one dimension. And so we've got a mass 1 that's coming in here and a mass 2 that maybe is just sitting here. So here we'll have a V1 initial coming in here. And then we've got mass 2 that's just sitting there. And V2 initial is equal to 0. So it's at rest. And then after the collision, what's going to happen? Okay, we'll have, afterwards, we'll have M1 is going to have some V1 final. And we don't know the direction of this, but it should come out in our conservation equations. Oh, and this is has a mass M1, and this has a mass M2, and I'm going to leave those as variables for a little while, and we'll imagine different scenarios. And then V2 final is going to head off in this direction. Okay. Actually, we kind of know that V2 is going to be heading to the right because it can't pass through, or M1 cannot pass through M2. Okay, they're not ghosts and they can't do that. So that'll be the situation. Now, before the collision, my total momentum will equal M1 V1 initial. After the collision, my total momentum will be M1 V1 final plus M2 V2 final. Okay, so I've got two things making that up. And I've got two unknowns now. I don't know V1 final and I don't know V2 final. So I need more information. And that more information will come from the fact that I was told this was an elastic collision. And what that means is their kinetic energy is going to be conserved. So the kinetic energy that M1 came in with, which is going to be 1/2 M1 V1 initial squared, that'll equal the final kinetic energy, which is going to be 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. Now, this is kind of scary. We've got a couple of expressions that have a lot of little variables hiding in them, and we're going to try to solve this for V1 final and V2 final. And so I'm going to start a new piece of paper, or actually I think I could just continue this one on down on a new piece of paper. Try to take as much advantage as I can. I shouldn't have started this on a dirty sheet of paper to begin with. And I don't expect you to follow through this, but the result that we get, we'll be able to learn some stuff from it. And maybe you could do this. Well, the first thing I'm going to do is with each one of the equations, I'm going to get the M1 terms on one side of the equation. And so with the momentum equation, I'll have M1 V1 initial minus M1 V1 final is going to equal M2 V2 final. So I just took this equation and brought that over. Then I'll do the same thing with the kinetic energy equation, except the first thing I'm going to do with the kinetic energy equation is divide everything by 1/2 or multiply everything by 2. that'll get rid of those 1/2 on each term, because since every term has them, I don't really need them. They don't tell me anything new. And then I'll subtract the thing over there, and I'll get M1 V1 initial squared minus M2 V, or M1, excuse me, V1 final squared is going to equal M2 V2 final squared. Okay, well, I've got things I can factor out of these. And I'm going to factor the M1 out on this side. I'll have M1 times V1 initial squared minus V1 final squared. And over here, nothing changes. There's only one term. So then I'm going to factor the M1 out of this one and write it underneath the other one. So I'll have M1 times V1 initial minus V1 final. Now, this is complicated stuff that you should be able to follow it. It's just algebra that I'm doing, but the motivation behind it, you may not know. But anyway, I'll have M2 V2 final. Then you can do the same thing to both sides of an equation. Like when you're doing algebra, if you've got an expression that looks like 7x, or no, yeah, 7x is equal to 21. It's okay to divide both sides by 7. You'll still have the same equation, and you'll get x is equal to 3. Okay. I'm going to divide the left side of this equation by M1 times V1 initial minus V1 final. Okay, and I'm going to divide the other side by the same thing, except M1 times V1 initial minus V1 final is equal to M2 V final, V2 final. So you can divide one equation by another equation, left side by left side, right side by right side. That's a legitimate operation, as long as they're equations that you're dividing by. They just happen to look different. Okay. Well, what happens on the left side is the M1s divide out. What happens on the right side is the M2s divide out. And then here I've got V2 final squared divided by V2 final. That's just V2, or V2 final. So I will have an expression for V2 final. And what have I got on the right, on the left side? Well, any suggestions? Turns out you can factor the top of that. That's the difference of two squares. And what it ends up being is V1 initial squared minus V1 final squared is V1 initial minus V1 final times V1 initial plus V1 final. Holy smoke, you never thought you'd have to see that in a physics class, but there's a reason that math is a prerequisite for this class. And then on the bottom, we've got V1 initial minus V1 final. Well, look at this. Those divide out. And what I get is V1 initial plus V1 final is equal to V2 final. Well, that's kind of nice. That's a third equation, but this is something I can take and drop into this equation. Oh man, this is getting kind of scary complicated, but let's see what we get if I drop this into here. So now I have M1 V1 initial minus M1. See, the problem with this equation is I still have two things that are unknown in it, but it's a new relation between those unknowns that I didn't have before. M1 V1 final is equal to M2 V2 final, but I'm just going to take that M2 and multiply it by both those things. M2 V1 initial plus M2 V1 final. And then I'll get the V1 initial terms on one side and the V1 final terms on the other side, and we'll see what that gives us. Let's see, bring the initial over there. I'll have M1 V1 initial minus M2 V1 initial, and that'll equal M1 V1 final plus M2 V1 final. And now, supposedly I would know V1 initial, and I'd know M1 and M2, but what I can do is factor, I guess. So I'd have M1 minus M2 times V1 initial, and that'll equal M1 plus M2 times V1 final, and it tells me this. V1 final is going to equal, I'm just solving for it here, M1 minus M2 divided by M1 plus M2 times V1 initial. Okay, that is pretty powerful. Now I can figure out all kinds of stuff. For instance, if M1 is equal to M2, okay, in that case, it would be like one pool ball hitting another pool ball. The first pool ball would stop, and this is if it hits it center on. If you hit it a glancing blow, they take off in two directions. But if M1 is equal to M2, the numerator is 0, so that makes V1 final 0. You may have done this playing pool before. You shoot a pool ball at the other one of the other ones, and you hit it straight on, and the first one stops and the second one takes off with the same speed that the first one came in with, which we haven't shown yet. But that's something that's kind of interesting that comes out of there. And then I've got an expression for V2 final. V2 final is equal to V1 initial plus V1 final. Well, V1 final is this thing. Let's see if we can simplify an expression for V2 final. That means you'll have V1 initial plus M1 minus M2 over M1 plus M2 times V1 initial. Now, I know this is really mathy, but let's just see what we get with it. Over on this side, I've got two V1 initials. So V2 final is going to equal, going to factor that out, and I will have 1 plus M1 minus M2 over M1 plus M2, and that's times V1 initial. Okay, we're almost there. 1, I can rewrite as, this will be V2 final. I'm going to get a common denominator. Okay, my denominator is going to be M1 plus M2. 1 is equal to M1 plus M2 divided by M1 plus M2. And then I'm adding to that M1 minus M2 over M1 plus M2, V1 initial. And when I add these two together, what I get is V2 final is equal to, well, I can just add these numerators together. I get M1 plus M1 and M2 minus M2 on top, which ends up being 2M1 divided by M1 plus M2 times V1 initial. I can figure out the speed it came in here at. And here's what I get out of it. If, let's see, if M1 is equal to M2, the bottom is going to become M1 plus M2 or plus M1, which is 2M1. I've got that in the top. If they're of equal mass, the final speed of this one ends up equaling the initial speed of this one. So what you have happening is one comes in, these are identical, the identical situation, hits 2, which is initially at rest. After the collision, 1 is sitting here at rest. This is V1 initial. And V2 or M2 will be headed out of here. Didn't draw it very well. And its final speed will equal V1 initial. So this is the thing that you might have done playing pool if you hit the thing just right. The ball will come in, hit an identical one. The first ball comes to rest and the second one takes off just as fast as the first one came in as, if it's an elastic collision. Pool balls aren't exactly an elastic collision. There's a little bit of energy lost because you can hear it. It takes energy to make sound. Something else that can come out of here, we didn't do it for a more general case, which is actually scarier than this, but something you can find out is that when you have two masses and you have an elastic collision, what you end up with is that the speed of approach, which ends up being the difference in their speeds, ends up equaling the speed of their separation. And the speed of their approach would be, if you imagine that they're both moving. So you've got one here and it's coming in with V1 initial, and you've got maybe mass 2 is heading out this way with a V2 initial, and V1 initial is bigger than V2 initial, which means this one's gaining on the other one and they're going to collide. Well, the speed of approach is going to equal V1 initial minus V2 initial. Okay. After the collision, you'll have mass 2 headed out this way with some V2 final, and you don't know what mass 1 might be doing, but it could have bounced off. That'll depend on the masses, but it'll have some V1 final, or it may still be going in that separation, but the speed of separation and after this we're going to stop. The speed of separation will equal the difference between these two in the opposite order. So it's going to be V2 final minus V1 final, and these two things are equal to each other. V1 initial minus V2 initial is going to equal V2 final minus V1 final. Now, this is only true in an elastic collision where you have the kinetic energy equaling before equaling the kinetic energy afterwards. But this can happen in some situations. We'll do a few more conservation of momentum things on Monday. If you want, we can look at some. And then I'll have some test review material that I'm going to be posting maybe later today. And we'll have that we can be taking a look at next week as well. So, whoa, that was our last day of really new material. And I know that last stuff was kind of mind-boggling. Maybe the right angle collisions were as well, but I hope you were able to follow through that. And otherwise, do you have any questions? Okay, well, have a good weekend. Start doing homework, start studying, reviewing for our final test, and be watching for the material I'm going to post for review stuff. Have a good